So one more situation. We have here a spring constant K. We have a mass, and we lob it that way. It comes in contact with the spring. It compresses. No friction, ice world. Okay? So it's happily going along at V0. It encounters the spring. What will happen? Spring will compress, and at some point, the block will momentarily come to rest. So all the kinetic energy will be converted into spring-stored energy, which we call elastic energy. Okay? And I want to know the form of that expression, so I'm going to cheat. Yeah, let's say I don't know that. Okay, so we know that the force and it seems to me that I need units of energy for energy. Seems reasonable. Okay, so U for the spring, the dimensions of that have to be what? Mass. It has to be, well, let's look at it from the point of view of our definition. So we had 1/2 mv squared. So that's 1 factor of mass, 2 factors of length, and inverse 2 factors of time. So I got to figure out how to combine a delta x and a k in the right combination to get this. So what are the dimensions of the spring constant? So that's mass. It's a force per unit length. So that divides the length out. And of course, delta x is just a straight length. Oh, this is child's play. Clearly, I need 2 factors of delta x and 1 of k. So I can say that the spring force is proportional to k times the compression squared. But I don't know from dimensional analysis what the proportionality constant is, right? So I can make up something. Like, I don't want to use K. I already got that. So C sounds good to me. C, K, delta x squared. Now, how can I use energy conservation to figure out what C should be? So if I add together 1/2 mv squared plus ck delta x squared, right? X dot would be the kinetic energy. Okay, this is going to work. That should be a constant. Okay, for you German speakers. So I now want to say, let me measure x from the uncompressed position, the equilibrium position of the spring. Okay, so then I have, okay, measure x from equilibrium, length of spring. So if I do that, then I would have 1/2 x dot squared plus some unknown constant kx squared is equal to that constant over here, which we could get basically from the initial velocity, right? Because all the energy initially was kinetic, so I could just set it to 1/2 mv naught squared. If it's a constant, then, Señorita de la Fuente, ¿qué quieres decirme?
No sé qué es palabra. I don't know what that word is before x.
Measure. Measure x from equilibrium length of spring. Oh, aren't we a critic? All right, so, okay, so the time derivative of this whole thing is the time derivative of a constant, L zippo, right? L zippo. So now we have to use the chain rule. So we have m. What's the derivative of this with respect to time, people? Don't forget the chain rule. Okay, so I have to say, I got a polynomial there, so I'm going to take the 2, pull it down, and that leaves me one of these, but now I have, by the chain rule, to take the derivative of the argument with respect to t, right? So that's x double dot plus c k times what? 2x x dot. Do you see there's a common factor of x dot that I'm going to factor out? X dot times m x double dot plus 2ckx is equal to 0. But kx was the force. Kx is the force of the spring. This thing looks like ma, right? So if F is equal to ma, now remember, which way is the spring force? It's that way. It's the opposite to the direction of F. So if I were to look at an isolation diagram, I have a force. I guess I'm supposed to put it the other way. I have a force on this face that is equal to kx, and x was positive that way. So F equals ma here says mx double dot is equal to minus kx. So in order for this to be 0, what must C be? Okay, in order for this whole thing to be 0, I can't count on x dot. Only once can I count on that. Therefore, the stuff inside has to be 0. Therefore, Therefore, 2ckx has to be equal to minus mx double dot. And this, therefore, has to be what value? 1/2. That's not right.
That's not right. Because mx double dot is negative k. So when you sub that in, you get the negative side. That's fine. Yeah.
Do I need a negative? Did I screw something up? Let's see here. This is good. Okay. Right, because from here, right, this is supposed to be equal to kx. Agreed? If this is the right expression, then minus mx double dot is equal to minus kx. So minus 2 wrongs make a right. I have kx. So 2c kx has to equal kx, 2c has to be equal to 1, c half. Okay, so therefore, finally, the spring potential energy, 1/2 kx squared, which we got out of a combination of dimensional analysis and ledger domain with calculus.